In this video, we're going to be looking at vectors in R and how we can use those vectors with arithmetic operations and other common functions. A vector is a data structure which consists of an ordered collection of cells or values, each of which have the same type, like double or character, etc. To create a vector, we're going to be using the C function to combine or concatenate an arbitrary number of arguments into a single vector. So for instance, if I would like a vector named x, and I want it to contain a set of numbers, I can use the C function like so. Type x, left arrow, C, and then I give it my list of arguments. So 4.1, 7, 1, etc. here. And then I'm going to type x in the next lines to output it. And when I run this code block, you'll see that we now have a vector of 6 elements. I can actually verify that there are 6 elements in this vector using the length function. So I type length x and run the code block, you'll see that it returns 6, which matches our vector above. Now it turns out in R that while we can create vectors using the C function, even scalar values like single numbers or single character strings are treated as vectors of length 1. And we can see this again using the length function. So if I were to type length with maybe 4.1 as an argument, you'll see that it returns 1, indicating this is a vector of length 1. So the C function can actually be used to concatenate more than just scalar values like we've seen. We can actually use vectors as arguments as well. So if I create a new vector y, use the C function to combine, say, x, 0, and maybe even minus x, you'll see here that we get the vector x printed out in order, followed by the number 0. And then we see that the elements of x printed again, each with the unary minus operator applied to them. Now this is a nice feature of vectors in that you don't always have to iterate through the elements of the vector to apply an operation. You can actually just use, say, an arithmetic operator on the vector, and it will automatically apply it to each element in the vector. So for example, I can say maybe it's 1 divided by x, and when I run this, you'll see that I get 1 divided by each element that was in the original vector x. One thing to note when you're applying operators, or really when you're working with vectors in general, is that the vectors may have different lengths, and you really need to take care to ensure that you get the results that you expect. Now you may have noticed in the previous example that this actually is a demonstration of this. That is, the scalar 1 here is considered to be a vector of length 1, and x is a vector of length 6, as we've already seen. So when I said the division operator was automatically applied to each element of the vector x, this is not some special property of scalars or the operator itself. Instead, R is actually replicating the shorter vector to match the length of the larger vector, and then applying the operation element for element. So let's look at an example to see how this works. If I create a new vector m with the elements 1, 2, 3, and 4, and then I multiply that vector by the scalar 4, just as in the previous example, the length 1 vector is repeated to match the length of the larger vector. So our scalar 4, being the length 1 vector, is repeated 4 times to match the length of the vector m. And then the multiplication between those two vectors is performed element for element, giving us a result 4, 8, 12, and 16. Of course, this is no different than what we just saw with the 1 divided by x. So let's now add a new vector, which has length 8. And for this, we're simply going to use the C function and pass m as an argument to it twice, like so. Now, when I run this code block, you see that the result is a vector of length 8, and its elements are 5, 10, 15, and 20 repeated twice. To get this result, there are 2 things to point out. First, the multiplication is performed first because the multiplication operator has a higher precedence than the addition operator. So just to remind you, I'll add a new code block and repeat that result here. And the second thing to point out is this result, which is a length 4 vector with values 4, 8, 12, and 16, is repeated twice to match the length 8 vector we created from repeating m twice, which looks like this. And so we can see here that the values 5, 10, 15, and 20 are the sum of 4 and 1, 8 and 2, 12 and 3, and of course 16 and 4. And similarly, the last 4 elements here are the sum of the repeated 4, 8, 12, and 16 with the last 4 elements of our vector here. In this example and the previous, the lengths of the vectors were either multiples of each other or they were 1. In these cases, it's easy to see how operations are performed element for element, even with replication. However, what happens when the lengths are not multiples of each other? Well, the answer to this is that the smaller vectors are fractionally repeated and then the expression is still evaluated element for element. Now, when this occurs, R will issue a warning to let you know. So let's see this in action. We're going to create a vector n consisting of the elements of m, which were 1, 2, 3, and 4, followed by two zeros, and then the elements of m again. This will give us a vector of length 10. Now, we're going to add the original vector m, length 4, to our new vector n, which has length 10, and then we're going to add a scalar to that, which is considered to be a vector of length 1. So let's run this code block. And the first thing we see is a warning issue, which lets us know that when we do m plus n, the lengths of these objects are not multiples of each other. This indicates that the fractional replication is being performed. Following that, however, is a vector of length 10, which is the result of m plus n plus 4. So let's see how this result comes about. First, let's start with the vector n. If you look down here, I have the vector n, and I've listed its elements off to the right. So you can see that the first four elements are 1, 2, 3, and 4, which are the elements of m here. This is followed by two zeros, just as we have here, and then again the elements m, 1, 2, 3, and 4. The scalar 4, since it's considered to be a vector of length 1, is simply repeated as many times as necessary. M, on the other hand, needs to be repeated 2.5 times, since 2.5 multiplied by 4 gives us 10, which is the length of n. And we see that here in that we have the elements 1, 2, 3, and 4 repeated fully 2 times, and then we have only the first half of the elements, namely 1 and 2, repeated here. Now, all we have to do is sum the columns here, and you'll see that we get the result as in the output of the previous code block. So 1 plus 1 plus 4 gives us 6, 2 plus 2 plus 4 gives us 8, and so on. And you'll see that this output here, which is the sum of these columns, matches the output from our code block exactly. Before moving on, I'd like to say a few more words about how these operations are actually performed on vectors. Now, we say that the smaller vectors are replicated or recycled, but this doesn't necessarily mean that the data is physically copied in memory. Copying the data would be inefficient and in some cases impractical. As such, really, the smaller vectors are indexed circularly using the modulus operator or some similar functionality to make it appear as if they've been copied to memory, but no copies actually occur. Later in this notebook, we'll actually discuss indexing in a bit more detail. But for now, we're going to move on to some common functions that you can use with your vectors. Okay, so we've already seen some examples using arithmetic operators on vectors. But R also includes a number of built-in functions that we can use as well. For instance, recall that the vector x had the following 6 values here. If we were interested in the sum of these values, for instance, we could iterate through each of the values, keeping up with the sum as we go, or we can use the sum function, and the sum function will automatically do this for us. Now, let's say that we really want to know not so much the sum of these values, but maybe the mean of these values. We could always use the length function that we saw previously to divide our sum by the length to get the sample mean. Now, we could write this every time we want the mean, but R does include a function that does this for us, and that's the mean function. This has the benefit of being simpler and clearer in your code, so people reading your code will know exactly what your intent was. Similarly, if we wanted the sample variance, we could write the full expression for this. But again, this is complicated and prone to error. We could make a mistake, a typo, for instance, in here, and it may take us some time to find it if we're not careful. So once again, R comes to the rescue and gives us the variance function, var, which, just like the mean, helps to simplify and clarify the intent of your code. The last two functions that I'm going to show you here are the minimum and maximum functions, each of which take a vector as an argument and simply return either the minimum or maximum value in that vector. So for the minimum function, we simply type min of x and run the code block. And for the maximum, we type max of x and run the code block. There are many other functions available to you as well, and we certainly can't cover them all here. I do encourage you to visit the R project website for more information, view the R base package manual for more functions like these, as well as descriptions and examples. And of course, you can always search online, as there are a ton of resources out there that can point you in the right direction.